Okay, we're going to get started with our last speaker for this afternoon. A little ahead of schedule here. We lost a couple speakers today. This gentleman is Dr. Casey Handmer. He's going to talk about developing an extensible roadmap for industrialization of Mars to full self-sufficiency. Let's give him a warm welcome.
Thank you very much. Oh, it's good to be here, and thank you for your patience in getting that straightened out. There'll be PDFs on Mars someday. Can everyone hear me? I think so. This is a pretty good system. All right. Well, I'm going to be covering quite a lot of material here, and I'm going to get onto some big ideas. And actually, I was very happy to see in the previous talk some stuff that kind of touched on what I'm going to be talking about, so you guys are all nicely prepped and warmed up. And I'm just going to start by pointing out that I really love this image that I've used as my background on the first slide, which is Gale Crater taken from the north by Mars Global Surveyor about 10 years ago. And I've looked at this picture 1,000 times. You've probably all looked at this picture 1,000 times. But it was only recently that I noticed that just above the final N in industrialization, there's actually a perfectly preserved river delta. Has anyone noticed that before? How cool is that? Anyway. I'm going to talk a little bit about me, so you know who is talking to you for the next 20 or so minutes. I have many interests. I did my PhD at Caltech in gravitational waves. I was interested in warp drives, and when I worked out that they're not really possible, I switched to engineering, and I worked at Hyperloop 1 for 2.5 years, and I was a levitation engineer there. The picture on the bottom right of that slide is the tube we built in the desert. We shot the Hyperloop down there at about 250 miles an hour. It levitated. It worked the first time, which was kind of cool for anyone who's ever built an engineering project before. And I currently work at JPL, although I must say as a disclaimer, I'm representing myself and not my employer here. And then there's a couple of pictures along the top with various interests. I hitchhiked through the remnants of the Soviet Union about 10 years ago and found that giant statue in the middle of nowhere. Built a Tesla coil once, and on the top right, I'm pointing at the Great Unconformity in the Grand Canyon, which is a 1 billion year gap in the geological record, which is pretty cool. It's a day's walk from the road. So I've jumped ahead of myself slightly, but I'm just going to start off by extending my disclaimer and saying that I don't have a crystal ball. I don't know for sure how to build a city on Mars. I don't know for sure whether, as we heard in the previous, at the end of the previous talk, whether Elon Musk knows all the answers or Rob Zubrin has correctly foreseen every aspect of it. I suspect that we know between us in this room large aspects of the problem, a large total, but we don't know everything there is to know. And actually this applies to all of us. We're mostly agnostic, we're mostly ignorant about the challenges that we will encounter when it comes to building cities for humans on Mars. We're not even, most of us, getting paid to do this. We do it because we love it. We come together once a year, this conference, we share these ideas, and then we take them out and we spread them into the community, like the conference flu. So the talk I'm going to give today is derived from a book that I wrote over the last year and recently published. You can find it on Amazon. You can find it on my website, caseyhandmer.com, and the book is as cheap as I can possibly make it. It's not my day job. I just want to get these ideas out there so you can read them in a format that appeals to you. The Google Doc is available for free on my website. Go there. If you think that I've said something wrong, I want to know about it. I want you to find something that you don't agree with, leave a comment, let me know. We'll discuss it, work it out. Because I know a lot of things, especially about arcane aspects of gravitational theory, but I sure as hell don't know everything, and I'm sure as hell still learning. So the goal in this talk is to think systematically about visions for the future, and I'm going to do that. I'm going to start really by defining autarky. And as you can see on the left-hand side of this slide, thanks to Google, it's defined as economic independence or self-sufficiency. It's a Greek root. And Google Trends shows that although this word was kind of invented in the early 17th century, early 18th century, it really wasn't important. It really wasn't a word that appeared very much in any literature until the 1930s. And the reason for that is that in the 1930s, all the current industrial powers were busily industrializing in Europe because they knew they were heading for World War II, and they knew that when push came to shove in the Second World War, as was borne out by past experience, the countries that were able to produce submarines and tanks and planes and bombs won. They prevailed. The ones that were able to produce them more quickly and more effectively prevailed. For the first time in history, winning a war was not merely a matter of hoping that you got lucky on the day or had more people to go into the trenches and die, like World War I. It came down to being industrially superior. And although I don't want to push this analogy any further than I absolutely have to, the surface of Mars is a lot more like World War II in that survival depends on being industrially competent than man versus wild, where survival depends on knowing what grubs you can eat, because there are no grubs on Mars. It's not possible to start there in a kind of ad hoc agricultural pioneer kind of way. And just to underscore this, I'm going to talk a bit about The Martian. So the top right there is a screen grab from The Martian. The Martian is one of my favorite films. I've watched it many, many times. It does have one particularly glaring error. In the opening scene, Mars is turning the wrong way. But I love the shot anyway. They should just put it the other way around. And so when we think of self-sufficiency on Mars, the first thing a lot of us will think about is this shot from The Martian. It's Mark Watney, it's Matt Damon there sitting there growing potatoes. And really, what I'm challenging you to think about in the next half hour is what would have happened if Watney did not have a ride home? And we know this because the book is quite explicit about it. He would have starved. But what if he'd had a larger greenhouse and had been able to grow more potatoes? What if his potatoes hadn't died on him? He'd been able to make potatoes for the rest of his life, the rest of his natural life. He still would have died. He would have died way sooner than he would have died of old age. And the reality is that even if he was well supplied, even if he had 1,000 friends there and gigantic greenhouses helping him out, no amount of digging potatoes and planting them would enable him to survive indefinitely, as is explained very clearly and succinctly in the book by Andy Weir, because his existence there depended on his water reclaimer and his oxygen machine and his power systems and all those other mechanical things, machines that go bing, keeping him alive as though he's a patient in hospital on life support. And once those parts break down, if there are no spares left over, it's game over. And this is what I'm getting at when I say that surviving on Mars requires industrial competence. And then just on the bottom right, I have a lovely picture of some greenhouses in Holland, which actually have the highest per area productivity of any natural light agriculture in the world. It's like a factor of 20 or 50 above, kind of the standard average agricultural productivity in the 19th century. So a factor of 50 times more productivity, which is incredible. But even those greenhouses transposed to Mars and made airtight and all that kind of stuff wouldn't be enough. All right. So, I've got my remarks mixed up. How should we think about industry in space? Who here has heard of Cody Reader or Cody's Lab? Oh, that's disappointingly few of you. Okay, well, you all have some homework. He's on YouTube. He has a channel called Cody's Lab, which has like 1 million subscribers. He's about my age. He's a little bit younger, and he lives in a fairly remote part of Utah. And he goes to university and he keeps bees, and he does all kinds of really cool stuff. He made hydrazine in his kitchen sink. I mean, like, the number of people I know who've done that and are still alive is a very small number. And on this lab, he's actually fascinated. He was one of the candidates in Mars One many years ago, and he's fascinated by the idea of living in space. He dug a mine in his backyard to extract metal and to pressurize and try and live in there by himself. And he demonstrates on camera for you a lot of the basis of primary production, including mining, farming, prospecting, chemical purification. He's a very, very clever and very accessible presenter. He's mostly self-taught. But even 1,000 Codys would not survive very long on Mars, because even though Cody, as a technical, well-educated person, and if you had a number of other friends helping him, would probably be able to make almost anything, a robot arm or anything like that. And there are people we know who are very technically competent, who could make anything. They often make them themselves. They build planes in their backyard, in the garage, right? The key distinction I want to get at is that even 1,000 Codys would not be able to make everything. They can make anything, but they can't make everything, at least as fast as it breaks down in normal use. And actually, this is pretty clear, because even in Cody's ranch, which is in near Grantsville in Utah, he and his family are not exactly well off, and just keeping all the machinery on their ranch running, which is not advanced industrial chip fabrication or anything, it's like a couple of tractors and things like that, is really challenging. And he can breathe the air there, there are fires and things, but Utah it's not the most hostile environment on Earth, but it's kind of borderline. So it's simply not enough to grow food. Living on Mars is a lot more like living in a submarine or in an aircraft carrier or in Antarctica or on the top of Mount Everest or something like that. The environment intrinsically will kill you very, very quickly. And so living on Mars will require a lot of automated manufacturing. It'll require an awful lot of metal. And so really when we think about this, we need to think big, really, really big. And I really love the previous talk, talked like we need 1 million people on Mars. I have the same kind of number in my head when I think about it, and I'll talk about that in a couple of slides. So the middle picture here on the top is the BlueScope Steelworks in Australia. It's Australia's main steelworks. Australia has about 22 million people. That's where I'm from. That's why I sound like Crocodile Dundee. BlueScope Steel here in just south of Sydney employs 16,000 people, and it produces about 3 million tons of steel a year. And that probably wouldn't be enough for a city on Mars that was capable of self-sufficiency, that had gotten to the scale where it was capable of producing all its own machinery and all its own food. Because, you know, consider the Gigafactory on the bottom right there. It produces cars and batteries. And Mars will eventually need chip fabrication and advanced composites and active industrial research. You know, think really big. This industrial park would take an hour or two to walk across, but that's not enough. It's just not enough. So my aim here isn't really to be entirely descriptive. I'm not going to show you a floor plan or a blueprint for what the Mars city will look like. I just don't know the answer to that. But what I would like to get across to you, if I can, is kind of a scientific method of thinking more about what are the right questions to ask rather than what the answers might be. Or how do we go about finding the answers to what we think are important questions rather than, and really what I hope from this talk is you walk away with a new strategy or a new question or a new idea rather than knowing for sure what all the answers will be. And this is my goal. So I wasn't initially sure that I wanted to put this slide in, but I decided I would because it is a topic that comes up quite a lot when people talk about building industry in space, and that is self-replicating machinery. And there's a nice cartoon there on the top right from a report by NASA on this subject, I think from 1980, before the space shuttle even flew. And wouldn't it be terrific if self-replicating machines existed? And 3D printers are really exciting technology, and my wedding ring is 3D printed as an example. And the reason they're really exciting technology is that they offer a shortcut compared to traditional methods of manufacturing things. You can do different kinds of things. It's like a new kind of tool. But 3D printers are not self-replicating machines. There are people who are trying to 3D print 3D printers, but they're nowhere near closure, and they probably won't be for a very long time. 3D printers have to have very carefully curated input material, and they can only make a subset of the possible parts that are needed to build things. They're cool, but they're not the full picture. Now, you might think that self-replicating machines are impossible. Just one of those things like faster than light travel or warp drives or something like that. It's just very, very borderline in terms of how we understand physics. This is not true. I'm a self-replicating machine. I thought there'd be a decent chance it wasn't here. My wife is currently 6 days overdue. But given the right resources, biological organisms reproduce themselves, right? Including my favorite on the left here, the platypus, the most inexplicable disproof of evolution ever thought of. That's obviously a joke. I hope that's clear. But the platypus makes eggs that contain baby platypuses, and on the bottom right there, E. coli produces more E. coli. And convincing an E. coli to print a CPU or a platypus to lay an air filter would be really something else. So when we think about self-replicating machines, we're not really talking about machines that reproduce only themselves. We're thinking about a factory that can reproduce itself and also produce anything else we might need, at least as quickly as it breaks down, which, in terms of existing technology, is nothing less than our modern globalized industrial society, at least until someone reads The Diamond Age by Neil Stephenson and builds a matter compiler. And I might emphasize there, the matter compiler is science fiction. People have talked about this for a very, very long time. There are many books about it, but no one's ever built one, no one's even got close. And there's a good reason for that. It's really, really hard. And if you could do it, that would drastically change all aspects of this, because then you just drop a self-replicating robot onto the asteroid belt and knock up a Dyson sphere in 2 months. It's a different kind of picture. So let's return to the original question, which is how to compactify the entire industrial stack and ship it to Mars. Let's talk about scale. This is a really, really big problem. It's a really big problem. So here's a list of the 25 or so most populous countries. The bolded ones, which are China, USA, Russia, Japan, Germany, and South Korea, in case it's too hard to read, are the only countries on Earth that within their own borders contain either a complete or essentially very, very close to complete industrial stack. And the reason I put an asterisk next to Russia is because it doesn't anymore, but it did until quite recently. So even a country of 144 million people and substantial technology can lose this ability. South Korea does, and it's the smallest in the list, but it is kind of sandwiched in a hammock, as it were, between Japan and China. And Germany does, but it's kind of at the nexus of a lot of other very advanced industrial nations, although those nations don't, at least not since a long time ago, have the ability to produce everything. And by everything, I mean container ships, fighter jets, computer chips, pencils, mobile phones, all the hard stuff, the stuff we have to import. So this data strongly suggests that a scale in the hundreds of millions of people is necessary to have enough labor specialization. And that labor specialization is necessary to have enough efficiency to support a complete industrial stack. And this is on a planet that we evolved to survive on. Every single one of these countries, you can walk outside and breathe the air. But launching 100 million people to Mars would be a major headache. So let's look at some counterexamples. Economically isolated countries such as Albania or Cuba, North Korea or Iran have every reason to attempt industrial autarky. And in many cases have tried really, really, really hard. Iran just unveiled their fighter jet. Building fighter jets is really hard. But even Cuba, which has a population of 11 million people and a very benign climate, all up, and ample natural resources, has not succeeded despite 60 years of effort, 60 years of concerted outward effort. It's very, very tough to do. Now, Cuba has many other challenges. I'm not saying that because Cuba couldn't do it, it's impossible, but I'm just saying, let's not kid ourselves. Australia, which has a population of 22 million people, is not even close. Not that they're trying to be, but it's almost unimaginable to think of that. So I think with further advances, it may be possible to achieve autarky on Mars with only 1 million people after 40 or 50 years of transport and building, but this would not be easy. For example, imagine taking Iceland in the year 2018. This is a country with 350,000 people and also conveniently relatively isolated from the rest of the world. But without imports, Iceland would regress to an 18th century standard of living within months to years. They'd run out of oil within months. And consider now the world's largest container ship, which is the OOCL Hong Kong, which can carry about 22,000 containers. That's equivalent to about 2,000 flights of SpaceX's BFR, just to put it in round numbers. So 2,000 flights is a lot of flights. So I figure that's about the same number of flights as you would expect in the first 10 to 50 years of sending them to Mars. So your challenge is to think of a way of making Iceland industrially independent from the rest of the world with one container ship worth of gear. That sounds impossible, but it's so much easier than doing it on Mars because it's a container ship. It already exists, and you can breathe the air, and there's fish and stuff there. So it's just a nice thought experiment. I'm saying it's completely analogous. It's a nice thought experiment. Iceland also has limited natural resources in some ways, but it's a good thought experiment. And people have lived on Iceland with all levels of technology down to absolutely nothing for about 1,000 years. So let's talk a little bit about how to increase human productivity on Iceland or on Mars by a factor of 100 or so. So we can go from 100 million people's work with only 1 million people. We're going to try and replicate Japan's industrial power in Iceland. The trick is the mechanization of labor, which is related to why whales have really big mouths, as you can see on the top left. So if we consider a pre-industrial agricultural society, such as the fields pictured in the bottom left, all the energy is derived from solar power, which is derived from photosynthesis, and so all the available physical labor is from human muscle. Therefore, the total output of the system is limited, fundamentally, by how much energy humans can digest in their guts, which is not very much compared to all the work that needs to get done. And the gap in GDP between industrialized and pre-industrial societies is a factor of between 30 and 60. And that reflects the gap in energy consumption as well. By freeing humans from the requirement of work, of deriving value from sweat off our own brow, a single human can control a gigantic, often gasoline-fueled machine, or even remotely program one, to perform labor on its behalf. Now, we've already seen that on Earth, a sufficiently well-motivated, knowledgeable individual can survive in many places with no resources whatsoever. Think Bear Grylls and Man vs. Wild. An industrial Mars will require the production efficiency of like 100 million people. So the fundamental problem for industrial human societies on Mars is a terrible shortage of labor, because there's nothing like 100 million people on Mars, not even close. So the fundamental problem the solution rather is to automate and mechanize and then outsource non-local tasks. There's no reason to do software development on Mars, at least lots of it. But by how much? So I'm just going to talk about this graph in the top right-hand corner of the slide, which is the manual mechanized continuum graph. It looks very complicated, but it's not. For any level of technology, there's an optimal blend of human and machine labor. This is something that apparently, people at Tesla have learned in the last year or so as they rolled out the Model 3. And as an example, consider a truck that transports stuff for Walmart. All the work is being done by the engine, but the human is driving it, because self-driving trucks don't exist yet. It's very, very difficult. It's much cheaper to put a human there. Same thing goes for planes and trains and cars. Take, for example, in the bottom right, I have the world's cheapest drill, which is that, I don't know, a Ryobi or something, 9.6 volts. That costs $20. And on the bottom right, I have the most expensive drill on Mars, which costs $2 billion. There's a difference of 8 orders of magnitude, and the drill on Mars sometimes breaks down for a year or so, but it doesn't require a human to line it up. And so when people say, well, we'll just build a Mars or a base on the moon or on Mars, we'll build it robotically and then humans will arrive and cut the ribbon. I like to think of the difference between a well-resourced contractor with power tools building a house by themselves in 6 weeks from prefabricated components and a steady supply chain and power tools, and trying to do anything with robots remotely. It is literally 8 orders of magnitude. Maybe NASA spends too much money. 7 orders of magnitude. It's not even close. And then the last thing I want to point out about this graph is that when technology improves, the optimum point on the manual mechanized continuum moves to the right. It doesn't move all the way. It moves a little bit. And if you want to derive additional technology development, you can move that point further to the right. But at any point, for almost any task, it's always better to start with humans doing the work and then kind of allow robots to take over the easy stuff. So how to do a Japanese level of industrial versatility and power with an Iceland-style population? We have to grow the fraction of labor that's automated as the base scales, right? You start off with a certain population, a certain team doing something. As the base scales, they'll have to produce more and more of that thing, whether it be fuel or water or food or anything like that. And the challenge is, can the same group of people do more stuff without greatly increasing the population? And the way they do that is they automate tasks. So for inspiration, and really the only case where this has been done already, let's consider programming languages. So this is only really cost effective in situations where there is such a profound labor shortage. And programming computers is a really great example, because keeping up with the capability and complexity of modern computers is just way beyond the capacity of an individual human. It's not possible to scale up the same programming techniques that we used for the Apollo guidance computer to modern computers, because they have literally like 10 orders of magnitude more processing power. So instead, we abstract. We put in layers of abstraction. And you can see this through the history of programming languages. The lowest in the hierarchy is machine code, zeros and ones, which I have here across the top. Does anyone read ASCII? You can look it up later. I put a secret hidden message in there. And then on top of that, assembler code, which abstracts above that direct bare metal thing. And then C, which enables more powerful operations and direct control of memory, but also the use of functions. And then C++, which allows, I apologize, some of you are probably not programmers, but take my word for it. C++ allows more levels of abstraction and templates and object-oriented coding. And then I use Python quite often day-to-day nowadays, because it enables a lot of C++ functionality with a lot more kind of human-friendly aspects, which basically saves me time, because my computer can work overnight, but I like to sleep at night. So I can get more done with a more powerful, more versatile programming language. So I don't really want to stretch this analogy too far, because ultimately manufacturing, as I've depicted in the bottom right there, is a little bit different to computer programming. But a nice way of thinking about this is that initially assembly of IKEA flat pack stuff on Mars is done by humans, but then over time robots are brought in that can perform aspects of that operation, and then some years later, when productivity needs to increase further, robots are brought in to build the robots that do that. And then over time, a lot of people on Mars end up spending all their time just assembling the most versatile robots of all, and assemble other robots that then assemble further robots. And this is why I think that although an American city, as Bob pointed out earlier, consumes about 1 gigawatt of power for 1 million people. On Mars, the energy consumption will have to be much, much higher, not only because there's no fossil fuels to burn, but also because the GDP, if you like, the economic and industrial productivity per capita will have to be much, much higher in order to produce all the things they need to survive. All right. So the final question I'm going to cover is the order of industrial rollout. So what resources get made first? That is, as factories are getting built on Mars, products that are not produced on Mars must be imported from Earth. But over time, you'll want to produce more and more products locally on Mars, and there's an order in which that should happen. And I can't tell you exactly what that order is, but there is a way in kind of ranking these things in a sensible way. And so as a case study, I just kind of looked up this robot arm here, which happens to be an open source robot arm. I think this is a really fabulous thing that people can obtain open source code, in this case, a design for a robot arm. Anyone can go out and buy these materials and the code and build it in their backyard and run it. And I think that's a model for how dedicated amateurs, essentially like myself, can contribute to an overall effort to industrialize places like Mars. It's by doing work in our own time and giving the product away. So this giant kind of table here that looks rather dull is the bill of materials, which is basically a shopping list to build this robot arm. There's a lot of stuff in it. Actually, this is only about half the bill of materials, but I couldn't fit it all on the slide. So broadly speaking, components for this robot arm fall into 5 different types. Structure, which is like bones, and then fasteners, which is bolts and screws and things, and rivets. Bearings, which are the ball bearings, things that enable parts to move past each other. Motors, which provide the motive force and move things around. And then finally, power electronics, things with copper in them, things with silicon in them, things that take the power out of the wall and then put it into the motors in a sensible and intelligent way that allows the robot arm to move in a way that we just see as natural because our own arms do it, but it's very unnatural. And if you've ever built a robot, they spend most of the time punching themselves in the head. So I tabulated in this graph the cost as a proxy for the manufacturing difficulty and its mass as a proxy for the transportation difficulty from Earth. So ultimately, I think on Mars, you'd want to build the really heavy stuff that's easy to make first, and then over time, kind of work your way down towards stuff that is much lighter, so easier to ship from Earth, and much, much harder to make. And probably the lightest, most difficult thing to make it's probably a human brain, and then closely followed by computer chips. And it turns out that the order in which the components of this robot arm would be produced in this kind of paradigm that I've introduced is exactly the order I introduced them. Structure, which can be 3D printed or made of bulk materials, followed by fasteners, which have to be kind of quite tightly toleranced in order to work properly. They have to have pieces in the right places and be the right size. And then bearings, which again can be produced by machines. And then motors. And motors are an interesting case because on Earth they're quite cheap due to mass manufacture, but they actually require all kinds of weird heterogeneous materials. There's zinc and steels and magnets. Magnets themselves are made of rare earth elements. And they've got windings, and motors are really quite labor intensive to produce, but then obviously the power electronics is much harder still. Making nice sulfur-free copper is pretty difficult. It's quite expensive to do on Earth, but even that is much, much easier than producing like a Raspberry Pi or some kind of computer that can actually command the electrons to go in the right place at the right time. So this is the final slide. This is the one you've been waiting for. This is the roadmap for industrialization. There's an awful lot going on here, and I'm going to unpack it, and it's going to take me a few minutes. So what I was attempting to do with this graph that kind of struck me some moment a couple of years ago when I first started thinking about this problem, the problem being how do you go about putting 1 million humans on Mars in a sensible way, is what is the order in which the stuff gets made on Mars, and how does the population increase along that trajectory? So on the left-hand side of this graph, we have this kind of ladder of things. And I haven't listed all the different possible things there are to make. On Iceland's statistics website, there is 4,300 different products which Iceland imports. That would be a pretty good place to start if you wanted to try and think about all the things that had to be made to be imported or produced locally. And so if you think about things that are needed in vast quantities and pretty easy to make locally, the most obvious one is oxygen. And it turns out that without oxygen being produced on Mars, it's not even possible to fly home. So that's why on the horizontal axis we have population, and the bottom left we have only robots. They take a one-way trip, and they drive around for a while, and then, I'm sorry. once oxygen can be produced locally, it is actually possible to do a sample return mission, or to fly a limited number of humans to Mars, and then they can produce fuel locally, but, they can produce oxygen locally, but bring the fuel from Earth. It's not particularly optimal, but it can be done. And so that's why I've got these thresholds on the right-hand side of the graph, the return flight threshold and the efficient cargo utilization threshold. As we continue up this graph, I'll just read them all out. We've got oxygen for propulsion, we've got hydrogen, water, fuel, carbs, like some foods basically, plastics, masonry and concrete, metals. Metals can be further subdivided into structural metals like steel, and then aerospace alloys, of which there are thousands of different kinds of aluminium alloys that are more difficult to make. And then electronics. I've got pharma there as a kind of catch-all for complicated chemistry and weird chemicals. And then at the top, I've got basically everything. And that's a logarithmic scale in terms of mass. So every time you go up by one color block, you're making 10 times as much stuff locally, or the total fraction of stuff that has to be brought from Earth reduces by a factor of 10 on a per capita basis. And then the horizontal axis is log of population from robots all the way up to about 100 million. And so in the very top right-hand corner is what we all want, which is self-sustaining. It's the population. We don't know what the population is exactly, between 10,000 and 100 million, and they're able to produce everything. And then the red curve represents a trajectory, a potential trajectory. I don't know how this will really go, but it is a potential trajectory of how population scales with the ability to produce everything locally. And so initially, when the population is between 0 and 10, kind of in the exploration phase, you kind of go and come back, and then up to, say, 100 or 1,000, it's an outpost phase, which is a little bit like Antarctica. And on the bottom left is a picture of my lovely wife in Antarctica, where she spent about a year in 2016. And Antarctica is an interesting case because, like many of these advanced bases and military bases or submarines or aircraft carriers or whatever, people live there all year round. And they've done so since the 1950s. But they are dependent on an ongoing and pretty expensive investment on the parts of governments that think it is worthwhile to have stations down there for research and strategic purposes. And there's no way in hell that the Antarctic station could ever produce all the stuff it needs. Sure, it's got a workshop, and if a bearing blows somewhere they need a bearing, they could probably machine a new bearing by hand. But you'd have to be crazy to think that machining bearings by hand is a way to get to self-sufficiency. And I'm very happy to say that there are no plans by anyone to try and build a city of 1 million people on Antarctica to do this. But, you know, it's just a nice way of thinking about an intermediate stage of settling Mars. Now, the final kind of point inside this graph is that it would be really nice if, by increasing the population by a factor of 10, you were able to decrease the dependence of stuff on Earth by at least a factor of 10. But that's probably not likely to occur. In particular, when it's time to start producing things that require essentially all the elements, it's necessary to have a dedicated mine for all the different kinds of things that you need. And that requires a lot of people to be operating machinery in a lot of different disaggregated mines and remote stations that are able to produce these materials. And that's incredibly labor intensive, incredibly cost intensive. So it's quite likely that as the population increases, this kind of closure will gradually kind of curve over, as I've shown in the graph, until it reaches that nice purple dot. That purple dot is the cusp of settlement viability, because that's the point where it gets no harder. After that, it's all downhill. And really what that means is that Mars has the ability to produce all the stuff it could possibly need, and at that point it's just a matter of building more large pressurized volumes and setting up factories inside them and doing more and more complicated things with existing primary, secondary, and tertiary manufacturing feedstock, which I think is a really nice thing, and if I'm lucky, I'll live long enough to see it. So the fundamental limit to how fast this can occur, of course, you know, one could start at the bottom left of this graph and kind of gradually crawl upwards over 10,000 years. The rate at which it can occur is determined by the rate at which cargo can be moved to Mars, because as more cargo gets moved to Mars, more factories can be built, and the number of people as a fraction of the overall cargo can increase. So that is limited really by how fast rockets can be built on Earth. And there's kind of a thing which you realize when you're looking at problems of this scale, which is that there's not a problem in space that can't be solved by building a bigger rocket on Earth, where big rockets are really expensive, let me tell you, but the engineers on Earth are practically free compared to in space. So I just want to point out that today SpaceX builds about 20 Falcon 9 cores a year, which is not really enough to get this done, ever. But Boeing currently builds 560 737s a year. Now you're talking. There are companies currently operating on Earth today with advanced manufacturing capability, building machines at roughly the appropriate scale, cost and complexity, at the rates that are necessary to build a self-sustaining human city on Mars. It can be done. This is not something that's hypothetical. It's not something that's possibly forbidden by the laws of physics. It can be done. It can be done. So, in summary, I think autarky is possible, but it requires a really, really, really bold vision for scale. It requires lots of really giant rockets. It requires lots of people. It requires robots, really advanced robots. Robots are amazing, but they need to get much, much more amazing. It requires dedicated, continuing commitment and support from people like us, but also people who will be paid to do this full time on Earth, to the tune of like millions of people working on this over the next 50 to 100 to 200 years. It requires a lot of money. It does not require infinite quantities of money. I'm not precisely sure how much money it would require, but I think it's in the order of 10 to $50 billion a year, which sounds like a lot until you look at, say, F-35 development. This is, again, something for which there are mechanisms in the world today that could do it. It's just, we'll have to see if enough of the potential programmatic risks can be required by strategic development of technology over the next 5 to 10 years by several of the key industry players. So I would love to stand here for the next 12 hours and go into vast detail on all these different questions. But I think I think I've kind of hit the key points. And I'd really like to hear from you if you've got questions or comments. Here, you can hit me up on Twitter. I'm at CJ Handmer, or you can send me emails. You can buttonhole me in the street so you can ask me questions right now. Thank you so much.
All right. Let's go ahead with some questions.
Yeah, I really liked this talk. It's an excellent talk.
Thank you.
Because, well, you really laid out the difficulty with the concept of autarky. And in fact, autarky as a policy has virtually always failed on Earth. Nazi Germany, North Korea, etc. Autarky is not a good economic plan. What is a good economic plan is trade, because that allows you to take advantage of the maximum possible division of labor. And you may have read, there's a classic essay on the pencil where someone shows
Strauss.
that it takes 1 billion people to make a pencil. And it's true, it does, because if the various parts of the pencil, they'll take the little brass thing on the end there. It involves alloys from halfway around the world, and people had to build the ships to ship the alloys, and people had to drill the oil to fuel the ships. And so just making the brass ring on the end of the pencil take 1 billion people. And this is also one reason why the world standard of living has gone up as the population has gone up, as opposed to the reverse. So I think that, okay, this idea of Mars as an autarky, and Musk has sometimes said this, we're going to put a colony on Mars so it will be a lifeboat if the Earth is destroyed, is nonsensical. If the Earth is destroyed, the Mars colony will die, okay? It needs to be able to trade with Earth. It needs to be able to export things. I mean, you have it exactly right over there. You go for the cheapest bulk, heaviest things that you can easily make on Mars. So you can make fuel, oxygen, steel, okay, things like this.
Plastics.
Okay, but things that weigh a lot but are not that complex, food. But on the other hand, computer chips and other things, don't weigh much. They can be imported from Earth, and you need something to export. I think the thing that a colony of Martians will export is inventions, intellectual property. There'll be a colony of technically adept people in a frontier environment where they're going to be forced to innovate, and those will be licensed on Earth. The inventions will be licensable on Earth. So I don't think. What you've basically shown is that autarky is a very doubtful proposition, and
Certainly long term.
Yeah, and it's never a desirable proposition.
Yeah. So if I could jump in for a second,
Yes,
just
sure.
to continue the conversation. I kind of glossed over this point at the beginning. When I talk about autarky for Mars City, one nice way of thinking about it is if the rockets stopped coming, how long would it take for everyone to die? And I mean, it sounds kind of bleak. But if right now planes stopped going to Antarctica, everyone there would either have to try and walk to the coast or would die in a matter of years. Some tactical nuclear submarines are supposed to be able to survive for 5 years without, but being cut off for 5 years. But that's actually a really long time in terms of mechanical reliability for anything. Obviously on Mars, you'd want to have a situation where, for example, there was some sort of supply interruption. It wasn't the end of the Earth and everyone didn't instantaneously starve to death. But what I mean by autarky is that it becomes difficult to estimate how long that period is. So if Mars is able to produce, and I don't mean like a billion of the latest Intel chips per year, but I mean a 8086 processor that's able to run a robot arm, which is adequate to run the industry robotically, then when Mars achieves autarky, of course it will still be trading a lot, hopefully with Earth, unless something terrible happens, and I don't think it will. But rather, you say, well, if the spaceship stopped coming, I couldn't tell you for sure how long it'll take us all to die. I think it might be essentially forever, which would be really cool. So that's what I meant there. In terms of trade, if it's possible to license stuff well enough that people will actually pay up, because it's very, very difficult. I mean, even today we have problems with kind of patent enforcement across the Pacific Ocean, let alone across 100 million miles of space. That is one of the best ideas out there, really. There's a lot of people out there who think that, oh, we can fund going to space by mining asteroids or something like that. And I've run the numbers on it. I've got blogs on it. I think that, like, if you think about, like, what would the value per gram of something on the moon have to be in order to make it worthwhile to go there and bring it to Earth? It might be valuable for use on the moon or on Mars or something like that. Mining on Mars is certainly valuable for use on Mars, but how valuable does something have to be in space to bring it all the way back to Earth? You're talking like the elixir of life. It would have to be something that, like, brings the dead back to life for people to be worth buying it. Like, there's nothing in existence which is that expensive except like tritium, and that's only due to pure scarcity and a real small lack of demand. Crack cocaine is not even close. So it's a really tough problem if you're trying to ask a question like, is it possible to get the money from space to fund this thing on Earth? And I think probably not, at least not for a very, very long time. But the amount of money required on Earth is also not an impossibly large sum of money. It's not so much that we all have to, ration our food. Does that answer any of your questions? Okay. Yeah.
Hi. Based on what you said about material stuff, in my humble opinion, the first few human crews on Mars should not be Mr. and Mrs. PhD scientists, but rather Mr. and Mrs. Fix-It, Mr. and Mrs. Electrician, Mr. and Mrs. Plumber.
I don't disagree. I didn't really cover that in this slide, in this talk, but I think that there's a point. I have a graph, I have a blog somewhere which talks a little bit like modeling in the previous talk, how rapidly can spaceships be produced, and given that, how rapidly can humans be deployed to Mars and their cargo be deployed to Mars. And I think that the first generation of BFR may be able to, with reusability and so on, get down to a price of about $350,000 per ticket, which will necessarily require those flights mostly to be supported by kind of space agencies, essentially, but then a follow-up generation of spaceships is much larger and has a larger payload fraction, when the population reaches about 10,000 level, may fall as low as $30,000 to $40,000 in today's money per ticket, which is enough that, I could potentially mortgage my kidneys and take a flight myself. No, I'm not kidding myself. I have a very narrow skill set. I don't think I'd be much use on Mars, but there are certainly, no shortage of people in the world who would have the skills necessary to install the first 10 or 50 IKEA flat pack things on Mars or whatever else needs to be done. That's actually a really interesting problem. I have a chapter of the book which talks about urban planning on Mars and talks about kind of a continuum between stuff that has to be collocated, like people's sleeping and eating areas and areas where they get healthcare and things like that, so they don't have to spend their entire days commuting back and forth. And then things that you really want to keep far away from other things, such as industrial processes that go boom and rockets landing and things like that. And it really kind of helps you think about what things go in the same pressurized dome or whatever, and what things go in the next one over, and what things go on the other side of the mountain.
Any other questions? Well, there's no
Not that
further
scary.
questions. We'll go ahead and end this last session here. Thank you, Dr. Casey Handmer.
Thank you so much.